Okay, so what we are going to do today is the sort of the, the first part of this one. We're going to discuss a little bit more about the capacitors. That's the sort of the definition that we left last lecture. And I'm going to just only show you how the Gauss's law, the concepts of electric field, electric potential, and everything actually leads to calculating something that we define as a capacitance. All right, just to show you. When I say just to show, because I don't think this kind of process will be put on the final exam, so you don't have to worry too much. But I will just discuss about this briefly, so you see the whole process. But for those of you that seems like the whole process is too much, you can just well, just grab some breakfast and just eat something along my explanation, and then just come back later. Oh no, not come back later, but I mean just in front of the screen. Okay, and once we're done with that, then we're gonna move on. All right, so we're gonna sort of like get out of the electric field, electric potential, the crazy stuff, and then we're going to introduce the something that you probably have done some of these already. It's the electric current and Ohm's law. Okay, so if I write it like V equal to IR, some of you might have already seen this kind of thing. So we're gonna review a little bit of that, and we're going to do the circuit analysis. But the good thing about the circuit analysis today is simple. Simple in the sense that once you understand the concepts of Ohm's law, you combine that with Kirchhoff's rule, which allow you to do the circuit analysis that one step harder than supposed to be just like a simple circuit that can be calculated through Ohm's law. So you are going to learn Kirchhoff's rule, which allow you to do some complex. Well, it's not very complicated. It's just more complex circuits. All right, and the process is very straightforward. So that's nice. So this one, I am guaranteeing you that once we sort of done this Kirchhoff's rule, you guys can do this problem 100%. As long as you do not make any mistakes. So you should be fine with this. Okay, and then we're going to finalize today's lecture with what happened if we just plug in that capacitors into the circuit. So we're going to have the combination of R and the C in the circuit. So that's why we name RC circuit. And then we're going to just look at some properties of this, which is not a lot at all. So it should be good. And once we have that done, then we close the chapter of electricity. Okay, sounds good? All right, so today's, I think, is quite doable, and more than half, it's like a recipe that you can follow very easily. Okay, all right, I'll try to keep the material light, and then you don't have to work too hard as last lecture. Last lecture was tough. Okay, all right, so let's take a look what we have. All right, so let's come back to capacitor again. Okay, so what we introduced last time was like, okay, so now we know what's going on with the charge, what's going on with the field around the charge, and what's going on if you would like to calculate the potential around electric fields and everything. So there is one device that you can create to store charge. That's why we named it the capacitor. It has the ability to store charge, so it has the capacity to store charges. Okay. However, the structure of this device is very simple. So you have something that can conduct electricity. So the easiest possibility was just you have, like, we call it the parallel plate. So you have two plates. It's like a metal plate. It could be anything conducting. So in general, of course, when you have just two plates, it's neutral. Okay, there's no charge on it. So what you can introduce through it is just introduce like a potential difference. For example, I can just put the battery across. Okay, once I put the battery across, what you get is you're gonna get the transfer of the charge. Of course, because one side is positive, one side is negative, so there is a charge flowing between these two plates. Okay, so when there's some sort of like some flow, at the end you're gonna end up with left side of the plate to be more positive than the left side, than the right side of plates. That makes sense? Okay, because you put the positive end on the left, negative end of the battery on the right. So the electron will flow from from left to right. So the right-handed plate will be more negative. Okay, so you generate something that looks like this. So that means there's one side of this one go positive and the other one go negative with the same amount, because it's just a transfer of the charge from one side to the other side. Okay, so once you have that, of course, if you think in terms of electric field come out from the positive charge and ends on the negative charge. So it looks like there is an electric field lines as shown in the figure. Or if you can think in terms of the potential difference, of course, there will be a potential difference across, because one side is positive, the other side is negative. So of course, the positive side will have a higher potential than the negative side. See, so everything is pretty much like on the concepts of field, potential, and of course, everything generated by charges. Okay, sounds good? All right, now, from the perspective of the capacitor, what we care about is that Q. We want to know how big is this, because we would like to utilize the stored charge, the charge that has been stored on this one. Okay, so that's why what we are going to define, just like I showed you last week, is we want to know the ratio, how much charge will you be able to get per unit of the voltage difference. When I say per unit, means you want to know the relationship between the amount of charge and the potential difference that it can generate. The reason that we care about this too, because that tells you how easy it is for you to bring the charge and put on one side, and of course that would be the opposite charge on the other side. So if you can get the ratio of this one, okay, so you can think about this, like if you fix the potential V, okay, and you have like two capacitors, one has a larger Q than the other, so you say, oh, the one that has a larger Q, that must have a larger capacity. Yeah, it seems like it has a bigger room for the charge to store on it. Okay, something like that. All right, so that's why you care about this ratio, the amount of charge that you can put on the device per voltage difference across the plates. We define this as the capacitance C. That's it. I hope you see the logic here. All right, or you can explain this in terms of the amount of charge that you can calculate on one of the two sides of the capacitor is just a product between the capacitance and the voltage across them. Okay, and just want to confirm one more time, you can write the V or the delta V, they mean the same thing. It's a potential difference. Okay, but once again, I don't, with some reason why, when we talk about the devices, when we talk about the circuits, they drop the delta sign most of the time. Maybe they just don't want to keep drawing the symbol or something. All right, so you can write it as the V, or you can write it as the delta V. They mean potential difference. Okay, all right, so the unit of the C, of course, is going to be the coulomb per volt, because the charge has the unit of coulomb, the potential difference has a unit of volt. So the coulomb per volt, we have that special name for it. That's the farad. Okay, is shorted from Faraday. So the unit of capacitance is farad, and we use the capital F for that. Okay, and then if you look at the figure, this one I just show you, I think you probably have seen this in so many places, on the motherboard, in the PC, on the circuit board, on any electrical devices, all this stuff. All right, and it comes in different shape and form. You can see that. I think the one that's most common one is like a cylindrical shape. That's the one I think that you saw the most. And I think maybe the coin shape, that's the one that you probably have seen them too. Okay, all right, so every time you see this, these are capacitor all the time. Okay, now for our purpose, what we want is this. All right, actually, I have showed you how to calculate the capacitance of capacitors in detail before in previous uh, trimesters, and it's not working. You guys sort of confused even more. So that's why, okay, for those of you that sort of like keen toward, how things sort of like, get to this point, yeah, just listen to me for maybe 5 more minutes or maybe 10 minutes. But for those of you that just like, Ajahn, I don't care. This slide summarize 3 shapes of the capacitors. Okay, so let's go through this one. Shape number 1 is, we call that the parallel plates, because it's just the 2 plates, 2 conducting plates put side by side, and that's it. Okay, this is the simplest one possible. And if you ask, well, Ajahn, if I know the size of the plate, right? If I know how big is the plate, and I know the separation between the plates, I can calculate the capacitance of this plate from this formula. And that's it. Isn't that nice? So the capacitance of a parallel plate capacitor is just, okay, there is some constant epsilon naught, which is the same epsilon naught that you saw from the Gauss's law, same epsilon naught, times the area divided by the separation, and you're done. Believe it or not. Nice. Okay. And number 2, if your parallel plate has been sort of like wrapped around and it formed like a spherical shape. So you can think of this as still parallel plate, but it's a plate that has been sort of, turn it into like a spherical in 3D. But of course, there's still one positive and one negative. It still keep the concepts of one side positive, the other side negative. If you have the spherical shaped capacitor, then the capacitance can be calculated through this formula. And of course, you can roll it into a cylinder. So you have the inner one positive, outer one negative. It still have one side negative, the other side positive. Then the capacitance is following this formula right here. Okay, so this is kind of weird. You probably think, well, Ajahn, usually you don't list the formula before. But this one is like you come in like 3 like formulas in one page. The point of these 3 formulas is this. Do you notice something here? For the parallel plates, the capacitance depends on how big the plate is and the separation between the plates. For the spherical, it depends only on, see, the 4 pi epsilon naught, which is constant. But it depends on the radii of these 2 spherical shells. See, the A is the inner radius and the B is the radius of the outer spherical shell. The third one, in the cylindrical case, it depends on how tall is this cylinder. And once again, it depends on the radii of the outer and the inner cylindrical shells. Okay, do you see what's the point of this one? The point is, the capacitance depends only on the physical shape of the capacitor. I think that's the key message to take home. All right, and don't worry about the derivation of this. Because, well, I'll show you. I mean, I'll let you know what the process of going through this one. But the point is this. The thing is, it depends on the size, the configuration of this shape and all this stuff. Once the size or the configuration of the physical shapes change, you change the capacitance of it all the time. And this allow you to, now you understand why. Here, let me give you this. Let me grab this quickly. There we go. Keyboard right here. Okay, so every time you punch the key, what do? What you did was you press the key. You actually looking at this, and then when you squeeze it down, you change the D, the separation between inside this, underneath this key here, there will be 2 plates. It might not come in a plate anymore, but there is a 2 conducting plates very close together. But once you press it down, it seems like you press it down onto these two plates as well. So you change the D. So actually what you did on the keyboard was just changing the capacitance of that key. So of course underneath this there will be a circuit that's checking which key has been pressed by checking which key has the capacitance changed, and that's it. That's how the keyboard works. Okay, this is one of the reasons why the keyboard doesn't really take electricity at all. You can just plug in, well, of course, just a common keyboard doesn't need electricity to run. Okay, so because you just check the change of the capacitance. Okay, sounds cool. All right, but not only that, the key is, if you remember, I think you remember back in the day that when you watch your TV at home, you need to use that antenna. Okay, and of course when whatever the screen just dropped and everything, you want to adjust your antenna to make pictures clear. When you touch the antenna, the picture might sort of like it's getting sort of like clear and everything, but once you let it go, the picture fails again. Yeah, you probably have experienced this kind of thing. Or actually you don't even have to touch it, you just walk passing your antenna on your TV, there will be like a screen shaking along with it, like there's like a ghost effect or something. All right, the reason for this is because when you have your hands touching the antenna, or when you have your body close to that antenna, actually the capacitance of that antenna actually changes. Why? Because the physical configuration of that antenna has changed. That's the whole point. Okay, this is the reason why the capacitance change along with the physical or configurations of the device get changed. The C will change along with it. Okay, and that comes to this smartphone. Okay, so the smartphone, actually, if you look at the box and the specification, I think maybe right now they don't care anymore, but back in the day, the screen, they say this is the capacitive touch screen. The reason is a capacitive because the touch screen actually use the capacitance change in the same way as the keyboard. So on this screen, all right, of course there will be like a lot of pixels on here, but underneath it, it will have some layer that acts just like the layer underneath the keyboard. When you have finger on it, you will change the C, the capacitance on that matrix of this pixels on here. All right, so of course you can check which part that you have the finger on, the C around that area will change along with it. And with that, you don't need to touch it, right? Because that's the key. You just have to change the physical configuration around that capacitor. So that means by having your finger close by and not having your finger close by, the C on that pixels will get changed. And that's how you detect which portion of the screen that get touched. Okay, and this is the reason why you can put a glass layer on top, because you don't need to really touch it. You just have your finger around, the C will already change. So this is what Apple's patent. And with this, then you can do multi-touch. That was the first day that the iPhone came out, and people just scream at it when you can pinch, zoom, and everything, all the stuff. Okay, so that is the capacitance, that's change of the capacitance that's being used in the technologies today. Actually, a keyboard was already like many decades ago, but for the capacitive touchscreen was only like maybe a decade or so. All right, but anyway, that's good. So you can have the glass top screen. Unlike the Nintendo DS, if you remember Nintendo DS. So when you play the Nintendo DS, you have like a pen or something, right? But you can feel that the screen of the Nintendo DS is kind of soft. Yeah, you remember that? Yeah. The reason that it's soft because you have to put the pressure on it. So you have to dent your screen to make the resistance, which we're going to study a little bit later, resistance of the screen change. So that's why, of course, it's not very precise and it's not very quick. And you have to press it quite, you have to put some dents on it to change the resistance. And the multi-touch is, you can forget about it because the accuracy is really going to be really bad. And the bad thing is the screen need to be flexible. So that's why the screen is not going to be as clean as glass. Okay, so the screen is going to look like plastic, and then, you know, it's kind of matte finish a little bit and soft. Okay, sounds reasonable. I hope I get enough impression of what is the key property of the C. The capacitance C depends on the physical shape and configuration of the capacitor. That's the key. Woo! All right, cool. All right, so that's for those of you that want to grab maybe just the key expressions of the C. I think this slide summarize all of these three shapes. And for college physics, of course, we're not going to do other shapes than these three. Okay, we're going to focus on these three. However, how do you get to this? That is something is very interesting to me. Maybe not to you. All right, the process of getting to this, the value of the C for each individual case is that I summarize it into 3 steps process. Okay, first of all, you start from the Gauss's law that you studied last week. The purpose of getting the Gauss's law here is just to find what the electric field between the plates. Okay? Once you use the Gauss's law to find the electric field between the plates, back 2 weeks ago, you learned how to get to the potential difference once you know the field. Remember that? The one that I tried to explain why there is a negative sign on and on. So once you know the shape or the size, the directions of the field, you use this negative E dot ds with the negative sign, you can figure out the potential difference between the two plates. Once you get the potential difference the two plates, that is pretty much almost done, because by definition, the capacitance is just a ratio between the charge and that potential difference. That's it. That's a 3-step process that you can use to find the value of the C. Okay, sounds good. I will show you one case, and I think that's it. And if you are interested in other cases, then you can try that at home if you're really keen toward knowing how to get through this 3-steps process. But I'll show you the first one, and it's the easiest one here. So if I have a parallel plates capacitor, okay, actually you have already done this last week, okay, and well, you can go back and sort of remind yourself how it's been done. But I can show you right here is what we did last week was, remember that we draw like a box shape. Okay, let me draw it in 3D just to remind you a little bit of this. Sort of familiar, yeah? All right, and then we agreed that last week that the electric field coming out from like a straight 2-dimensional sheet of charge, or like you have a plane of charge, then the electric field will come out perpendicular to the plane of the charge. So that's why the electric field is pointing, in this case, downward, because the upper plate is positive, the lower plate is negative. So the electric field just shoots straight out from the positive to the negative one. Okay, remember we did this on the simulation as well. When I have an array of positive charge on one side and I have the array of the negative charge on the other, electric field seems to come out straight, okay, perpendicular to the array of the charge. Okay, so once you have this electric field coming down here, what you agreed last time as well, like the electric field inside the metal is 0. Okay, right, we agree on that. So that's why the only portion of the surface that you draw that will get non-zero flux is just the bottom surface. Yeah, okay. All right. On the top surface, because the electric field is 0, flux over here is 0. Flux on the sides, the 4 sides, has no flux because the electric field line does not penetrate through the side walls. So that is the only place that there is the electric flux going through is the bottom surface. And the surface will have the vector expression for that surface by drawing a vector perpendicular to that actual surface. you will get the area vector. So in conclusion, you see that there is the electric field piercing down. Let me name it E. There is an area vector, the black arrow, going down as well. So on the bottom surface, you can see that now the flux, the electric flux, is going to be just right here. Okay, let me write it green. So over here, the flux on the bottom is just E dot A, and it's just EA cosine 0. And it's just E times A. That's it. Okay? Alright? Alright. And with that, then I am done on the left hand side of the Gauss's law. Okay, so let me write everything in full like this. So this is your Gaussian surface. Yeah, the box that you just drew. Okay, so you drew a Gaussian surface in the shape of a box. And you said on this surface, you have 6 surfaces. Okay, the flux on the top plus the flux through the sides plus the flux through the bottom. That will be the total flux through this box. However, we just say there's no flux on top, no flux on the sides. You only have the flux through the bottom surface. And you already calculated to be E times A. Okay, cool. All right, and that's it. That's the left side of this one. You equate this to the right side, which is just the charge enclosed inside your Gaussian surface divided by epsilon naught. Okay, and you say, okay, Dan, last time you said the only charge that you're going to have to get to calculate this one is just the charge that you drew here. You only care about the charge that is inside the box. Okay, so let me name this amount of charge to be just Q. So if you know the amount of charge inside this box, you just put it there, Q. And now you're pretty much done. Cool. However, of course, because what we can say about this one is from last time, we can say because we don't know much about this, but we can define the density of the charge. So you can say if the area of that green surface is A, I can put the charge density, which is the charge per area multiplied by A, if I want to make it sort of cleaner. And we can call the amount of charge by looking at the density of the charge instead of the amount of charge. So actually, I can write this one as sigma A over epsilon naught. Cool. A cancel. So that means I don't care. The size of the box that you try to draw to calculate this one doesn't really matter because you already cancel them out. So that's it. The electric field is just sigma over epsilon naught. And actually this exactly what we did last week. All right. So if the results looks very sort of like familiar, that's exactly what we did last week when we have a charge on one side of the metal plate. And then we say, hey, the electric field coming out of it is sigma over epsilon naught. Woo, okay. All right. You guys still with me? Maybe not. That's all right. All right. So now that's the first step. Now you know what the electric field between the plate is. Now I move on to the second step. Once I know that electric field, okay, let me write it over here. Electric field is sigma over epsilon naught. Now that's an easy one now because we can now calculate the potential difference across two ends of this one. So let me mark here. Yeah. You can say this is like point P. Let's use point number 1 and point number 2. I want to know what is the potential difference between the two plates. So what I have to do is just to calculate the potential between number 1 and number 2. You guys with me? Okay. However, this is the easiest case possible, right? Because the electric field is constant. When electric field is constant in your head, you can think it's like a gravitational field. Okay, and the potential difference, so let me write it like V1 minus V2. Or actually you can do V2 minus V1, doesn't matter, because you know that the positive side will have a higher potential than the negative one. Okay, so that's no big deal. So what you care about is just potential difference between point 1 and point 2. It's just gonna be the E times D. You guys with me? Yeah, we got this one from maybe 2 weeks ago, something like that. All right, so think of like MGH, okay, but we get rid of the M. We just get the G times the H. You call them potential. So over here, that's it. So you know the electric field is sigma over epsilon naught times D. That's kind of nice. Okay, and that's it. So that's your second step. You know what is the potential difference between the two plates. Then you can dump this one onto the last step. So you can just say the capacitance is just the amount of charge over potential difference. And that's what you got from the second step. And all I need to do is just plug in everything. Sigma D, I flip epsilon naught to the top. Okay, but once again, you can always express the amount of charge to be sigma A, right, all the time. Okay, you always write the charge density multiplied by the surface area. To get to this last stop, your sigma actually cancels one more time. So what you get eventually is going to be sigma naught A over D. Sorry, not sigma, epsilon. Epsilon naught A over D. And that's it, you're done. Right here. Woo! All right, so this just for those of you that are interested in how to get to the C by 3 steps process right here. Okay, so recap what I just did in the past 5-10 minutes. First, I used the Gauss's law to evaluate the electric field between the plates. Okay, once I know the fields between the plates, I use the relationship between the fields and the potential difference by doing the integral against the field to get to the potential. Okay, when I say against, I just emphasize that it's a negative sign. So when I know the field, I can calculate the potential difference through this expression. But because this one is simple, electric field is constant, so I can calculate the potential difference very easily by just take the product between the electric field and the distance, E times D. I'm done. Okay, once I get the E times D, I get to the potential difference. My business is almost done. The capacitance is defined as the charge over the potential difference. But because you want the charge of the whole plate, so actually what you get is the charge of the whole plate divided by the V. You can express this amount of charge by taking once again the charge density multiplied by the A. But actually this A is the A of the capacitor now. It's the A of the whole plate because you want to collect them all. You want to know what are the total charge on the plates. Okay, even though I use the same A as the A on the Gaussian surface. But in this case, you want the charge of the whole plate. So you extend your A to cover the whole plate. And that's pretty much A of the plate itself. Once you take the ratio, cancel the sigma, you get the final results right here. And that is it. Done. Whoa, all right. I get the feeling, yeah. Even I'm talking about this one, I'm tired. So you guys probably like, oh, John, what is going on here? Okay, so don't worry about this one. The process that you are seeing here is not going to be in the exam, so don't worry about it. Okay, I just want to have you seeing this kind of calculations like once in the college physics course or something like that. All right, but for those of you that really want to try, but this is on the textbook, you can get to the reference text and then read through the examples here. All right, I put one more exercise. I mean, it's not, you don't need to do this. This is like optional. So if you really want to try it, you can follow this 3 steps process, all right, using the Gauss's law, to get to the electric field between these two spherical capacitor if you want. Okay, yeah, you get the feeling. Okay, once you get the field, you use this expression to calculate the potential difference between the inner and the outer sphere. You get the potential difference. Okay, once you get that, take the ratio between the charge and the potential difference. You get the C, and that's your result right here. All right, so you can do this for all three shapes that I showed you before. At the end, this is your conclusion page right here. Okay, sounds good? Sounds good, Min. We're just gonna sort of like pause the capacitance calculation here. All right, don't want to dig anything too deep into this. All right, just want to just show you. I don't know. Can I say a little bit? But that's what it is. All right, so I hope that is how you get to these three formulas for each shape by doing 3 steps process calculation. All right, but yeah, this is the reason why you have to study Gauss's law. You have to study Gauss's law. You have to study how to calculate the potential from the field, and then you combine it with the definition of the capacitance. Right? See, you need the other 2 lectures to get to this. All right, guys. Any questions up to this point? You know, probably like, woo, done. Let's get to the next topic. All right. Woo. So everyone's still all right? Okay, maybe. Okay. All right. So that's done for capacitance. Okay. Now, let's get to the easy part. Easier. Now, it's going to be a lot easier, actually. So once we have that kind of idea of, you know, field, potential, capacitance, then there is another stuff that you can learn about the electricity, and this is very close to everyday's life, is the electric current. Of course, you use the electric current all the time to run electrical devices. Okay, so by definition of the current, every time you see the current, you can think of the flow. If you want to talk about the water currents, that's a water flow. If you want to talk about the heat currents, that's the heat flow. Now you can do the electric current. That is the charge flow, the flow of the charge. So that's it. So every time you have a movement of the charge, and then you care about how things flowing, you can just put a cross section on. Okay, you just sort of like, hey, just sort of draw a surface, and then you just want to count how much charge going through. You can think of this like a windows, or you can think of this like a gate. How much charge is actually flowing through the gate. And if you count the amount of charge that's flowing through, okay, you divide it by amount of time that it takes to flow through, then you can actually quantify the magnitude of the flow. If the amount of charge per unit time is high, you say, oh, the flow rate is high, so that is a high current. Okay, that's simple. So that's by definition, it's just the charge per unit time, just like any flows. Okay, sounds good? And because, of course, the unit of this one is coulomb for the charge, second for the time, so the coulomb per unit time is ampere, coulomb per second. Okay, which very familiar. Okay, your adapter, your charger, is rated by how sometimes, I mean, you can read it through what is the maximum current that you can use that device. It's already written on your specification. Okay, sounds good? All right. But as I said one more time, because we define the electron to be a negative charge, which is too bad. All right. Every time we talk about the current flow, the sign has to go along with it. So that means a positive charge is flowing. So in reality, if you have a current flow through the right, it might be the electrons that actually flowing through the left. Okay? Because it's the actual stuff that actually flowing in your electrical device most of the time are electrons. However, In some system, there might be like a positive charge flowing, like an ion. You know, when you have like in chemistry, some ion, positive ion is actually flowing. So the current is defined in the direction of the positive charge flowing. Okay, so just so you know that in most of the scenarios, the current actually comes from the flowing of the electrons backward, opposite side. All right, okay, very cool. So what you have over here is, to get charge to flow, okay, you need some electric field, right? Think of it this way. So positive charge usually will not move if you don't have any force acting on it. To get this thing to move, you need to apply some electric field. That's E. Yeah, that's good. However, now we know every time you're going to generate electric field, there must be some sort of like some high potential, let me call V sub 1, and there must be some low potential, V sub 2. Okay, so that means every time you're going to generate some electric field, you must introduce the potential difference, because that potential difference eventually will lead you to the electric field, and the charge will move along with the field. Okay, so that's why, no doubt, you have to somehow generate potential difference, okay, to generate the flow. All right, now that means there is the relationship between the potential difference, okay, and the flow, that we call it the I. You can use the small I or capital I, doesn't matter. Okay, and it turns out the ratio between these two are linked through some constants, which makes sense. I mean, the higher the potential, you should get the higher of the current, something like that. All right, so this means these two parameters are related through some constants. So what you can think of it is like V is proportional to the I, or you can think in terms of the ratio if you want, up to you. So this ratio between V and R must be some constant, and that constant we name it the R, and it turns out to be a resistance. The reason it's a resistance because when you introduce it like this, you can see that I is inversely proportional to that constant. So the constant is bigger, it means the I must be smaller. So that's why we name it as a resist. It's a resist to the flow. It doesn't want to flow if the constant is big. All right, so whatever you can think of, this is just a ratio between the potential and the current flow that link through the resistance R. Okay, and the unit of the R is going to be volt per ampere, and the volt per amp, we name it the ohm, which is very familiar name once again. All right, amp is very familiar. Ohm, so that's not too bad. You have learned a couple times of this, and everything comes down to, oh yeah, actually this is already Ohm's law. I put it on this one. You can say I equal to V over R, V equal to IR, up to you, whatever you like, in any shape and form. Okay, this is just a relationship between these three parameters here. Okay, Ohm's law is good, that's fine. Okay, one thing that's sort of like very useful, this one is, once you know there is a current flow through some resistor, what you're getting is the power consumption through that resistor. That's something that you can calculate right away. All right, even though I can derive it for you guys, but I think the simplest idea is this. I don't know if you can follow this one very quickly. If I care about the power, this is a power. Power is just the energy per unit time. Okay, come along with me. But everyone remember, the definition of the potential difference is just the charge multiplied by the potential difference, right? That's by definition. Okay, U is the potential energy, okay, which can be found from charge multiplied by potential, no energy. Okay, very good. All right, so that means I can write the potential energy to be the product between the charge through potential difference. However, the charge per unit time is just the current by concept. So that means every time I know the potential difference and I know the current flow, the product between the current and the voltage or the potential difference is just the power. Done. So that's what you get. The power is just I times V. And then I can apply Ohm's law. V equal to IR. It's going to be written as I square R if you like. Or you can write I as a V over R. So you can express as V square over R. Up to you. Okay, but that's what you're getting from the do I have it around here? The adapter, right? Yeah. Oh, I have it here. So this is a car adapter. Okay. Which, wow, it's so small I can't see. Okay, so it says on here it's 5 volts, 2 amp. Right here. 5 volt, 2.4 amps. So that's, I think your charger is pretty much rated by like this, right? So in this case, my car charger is giving 5 volts across. It's a USB port, of course, 5 volts. And the current, it actually has 2 ports. One is 1 amp. And the other port is 2.4 amp. All right, and that's it. If you multiply this current and the voltage, you will get 5 watts for the 1 amp port, and you will get, what is that? It was what, 12 watts? Something like this. All right, so you know the wattage, right? So the power rating of this adapter. All right, and of course, you use this nowadays. When you buy like a charger, you have like super fast charge or something, you probably want to buy like 65 watts, maybe crazy like a 100 watt charger to do that super fast charge or something. All right, so that's how you calculate the power, which very easily calculated from the product between the voltage and the current flow. Okay, cool. All right. And okay, what I have example over here, if on the other hand, in some devices, you might not get like a pair of the voltage and the current. For example, in the light bulb, usually it's being rated through the watts of the bulb. Like you are buying a 2 watt bulb and it uses 1.5 volts, like it's being run on battery. Then you can trace back and calculate what is the resistance of that light bulb if you want to. Okay, sounds cool. All right, so in this case, this is your power, this is your V. You want to figure out the resistance, so you say P equal to V squared over R. So R is just V squared over P. And then you can plug in the number and you're done. Okay, so from now on, any electrical devices, you can figure out everything that you want, like what is the current flow, or if you want to know what is the power consumption, or if you want to figure out the resistance of that one, everything works through Ohm's law and the power in resistors. Okay, this is easy enough. I think you guys getting more happier, I guess. It's getting easier over time. All right, cool. All right, so I think this is probably these are things that you probably have already known, so that's nothing new. Okay, let's get to the business that I am about to lead to, which is how to do the circuit analysis. Okay, so this one you can lead through in terms of like, hey, you're gonna get energy out of it. You can think of this, think of that, but in reality, the actual devices that actually get connected can be written in terms of like a diagram. Okay, in a diagram. So that means something that tries to drive the current flow. You can think of it like a charge pump. That sounds really weird, but that's what it is. The battery, the AAA battery, AA battery, you can think of it like a charge pump because it's trying to pump the charge out from the positive ends of it and come back to the negative end that is pumped out again. Okay, so whatever the device that tries to generate the potential difference, you can think of it like it has the electromotive force. This is like a very, very old word. It's like a super old because it's like electron get moved by something pushing electromotive force. Okay, but I mean in reality we wrap everything up in terms of the potential difference. All right, but we still use the word EMF nowadays, all right, because it get the feeling of something being pushed out. That's kind of nice. But in your head, that is the equivalent of generating some potential difference. But because they still use electromotive force, so sometimes they just put like the notation of the E to be like the source of the potential difference. All right, so now you can use whatever you like, but in the back of your mind, you know that what you need is just potential difference being generated. Once there is a potential difference, then the charge can flow, something can move. Okay, all right, so that's the first part of it. And the rest of the stuff, you just have to draw a diagram to say that this movement of the charge, the flow of the charge, get through what kind of devices in the way. Okay, so this is what you get. The simplest case is just this. So you have a device that generates the potential difference. So let me draw it one more time here. That's the same as the potential difference generator. Okay, you can shorten say it's just the E, something that drive the charge. And then in reality, you will have like electrical wire. So that black line over there, that is just electrical wire. Then eventually you probably get this wire hooked up onto some devices. It could be your cell phone, it could be your TV, it could be your radio, it could be anything. And then you can represent that device to be something that's resisting. When I say resisting the flow, you can think in terms of the power consumption. So you can think of this resistor try to take away the energy from the charge that is flowing through it. Okay, so once you get to that one, you drive the other end of that to the negative end of your potential difference source, and this complete the circuits. All right, and that's we define how to write a very, this is the simplest circuits. It has the source generator to generate potential difference. You drive the flow within this circuits. That charge or that current will flow through the device that every device will have ability to take away some energy out of it. So you can name those devices to be the resistance in your way. So you put the resistance of that device R in your circuit, and we use the zigzag notation to represent some electrical devices. And once you have that, you have to complete the circuit. Otherwise, then there will be no flow because you don't know the other end of the potential. So you have to complete the whole circuit. So this means you can say it's complete loop. You have to have the whole thing in a loop. Okay. So once you have everything in the loop, then the current will start to flow. And then you can now, using the Ohm's law to calculate the current, you calculate blah, 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 on and on. Okay, sounds good? All right, so I think this is something that we're going to discuss for the rest of the class here. And it's going to be quite all right. Okay, just want to check first, guys. You guys familiar with this circuit? Yes? Any one of you haven't seen this before? Just to check. Yes. Okay. Yes. I mean, have seen this before, right? Okay. Very good. Okay. So if this is good, then the rest of the stuff will be quite all right. Okay. So if you have a circuit that looks as simple as this one, you can see that you can calculate the current flow right away by just take the E, all right, which is now equivalent to potential difference delta V, divided by R, and then you're done. That's it. Okay, because in your circuit, there are no other components. This is clean and clear. Things in terms of the actual flow of the charge. The charge will come out and flow. It's an actual charge. It's actually flowing. So there are charges that actually flow and actually enter into these devices and will come out. So because charge cannot disappear, if you put in 10, it will come out 10. If you put in 100, it will come out 100. So there's no doubt. Whatever the current that flow in, it will have the same amount as the current flowing out. So the current flow in your circuit is pretty much conserved. Whatever the current that come out it will have to come back. Okay, no disappearance of charges, impossible. Okay, sounds cool. All right, so that's why I can always imagine the flow of the charges to be just like the flow of water. If you send out the water and eventually that pipe lead you back, the amount of water will actually come back to you. It cannot disappear. You send out 1 cubic feet of water, it will come back 1 cubic feet. It cannot disappear along the way. Okay, same thing with the current flow. All right, so this is a simple one. All right, and the idea of this, well, or if the current is the same, what's changed? What actually changed is the energy. Think of it this way. You start out with the positive one, so that means this is high potential. And then the current just keep flowing here. Now it meets with some devices that take away the energy, right? Because it has some power consumption. So you can think of it like this device will lower your potential down. So when you come out, you will come out with the low potential. And of course, that low potential will just arrive here. So you can think of this that the charge actually give off some energy, or in terms of the potential will be lower through any resistor. So that means across any resistor, you will generate some potential across the resistor all the time. And the resistor will lower your potential. All right? And once you come out with the current with the lower potential, you arrive back at the negative ends of the battery. The chemical process and everything in your battery lift you up again to a higher potential. So that's why the battery, this one, the battery, we say it's the charge pump. It's like it's pumping the charge from a low V to high V. Same thing as water. If you let the water from high floor down to the ground floor, if you want the water to to get back up to the higher floor, you have to pump the water up. Same idea. Okay, so now you can always sort of like compare the current flow of the charge with the water flow. Pretty much the same thing. Okay, I hope you see, even though it's kind of redundant a little bit here, but I just want you to see that from the perspective of the energy consumption, if you want, all right, you come out with the high potential. Every time you go through resistor, it reduces that potential down, all right? And once you arrive back at the negative ends of the battery pump the energy up again. So think of it like lift up the charge, so the charge can start flowing downhill again, all right? Something like that. Okay, sounds cool? All right. When they say sounds cool, means here. So this is just the pictures showing you what happening if you have two, here we go, resistor in the way. Okay, let's think of it this way. Once again, you start with the E. The current get pumped out. Boom. Come out here. That's I. Boom. Now it get through the first resistor. If the resistance of the first resistor is R1, then you're going to get some energy taken away from the R1. So your energy actually reduced down by the potential across this R1. You guys with me? So that means you start high. When you get through the R1, your energy is dropped a little bit. But the current still flowing. Okay, still flowing. Get through the R2. Right? Every time the current flow through the resistor, your potential will drop one more time. How much? It's going to drop equal to the potential across the R2. And once you come out, you're going to come out with the current with a very, very low energy. And then just come back to the negative ends, get pumped up to the positive ends, and will start flowing again. Okay, so when it come out over here, you come with the full energy. That's a whole bar. When it goes through R1, V1 has been taken away. So your energy is reduced. Okay, and once you go through the second R, the R2, then the energy has been taken out completely. So you come out with nothing, and then you start going through the charge pump again, and the cycle just keep going. So that's complete the circuits. Okay, so let me ask you this. The reason I want to show you this one is, hey guys, what is V1? How much is V1? You say, well, Ajahn, this is easy. Because we just use Ohm's law. V equal to I times R. Yeah? So you take the I times the R1. And that's it, you're done. What about V2, Ajahn? It's going to be I times R2. Okay? But you already learned about the potential difference. If, let's say, I mark the spot here on this left corner to be spot A, and if I mark this one to be spot B, what is the potential across A and B? We say, well, Ajahn, that's easy because I know that A is connected to the positive end of the battery, B is connected through the negative end of the battery. So the potential between A and the B, let me take V sub A minus V sub B, is going to be E, correct? You guys with me? Okay. All right, very good. However, well, Ajahn, wait a second. Instead of looking at the bottom part of this circuit, can you look at the upper part of this one? I say, yeah, because it's still A and B anyway. So if you look up top, well, Ajahn, going from A to B along the upper part of this circuit, you have to go through V1 and V2. So that means V1 and V2 must be added to E as well. You get the feeling of what I'm trying to do here? All right. So that means by knowing this, this is how we can start to analyze the circuits. By looking at 2 points from A to B, you can figure out the potential difference across A and B. In this case, you can do in 2 ways. You can follow the bottom half of this circuit and say, oh, it's simple. It's just E. Or you can look at the upper half of this and it's just, oh, Ajahn, it's just V1 plus V2. But no matter which part you're talking about, it's still potential difference from A to B. So you equate these 2 paths and you say E equal to V1 plus V2. Isn't that nice? Okay. All right. So this is the basic of what we are about to do, is the circuit analysis. All right. But before we get to that, there is one cool thing that you can do from here. All right. This is review. I can write V1 or V sub 1 to be I R sub 1, V2 to be I R sub 2. Yeah, we just agree on that. I can pull the common factor, the current, because the current stays pretty much the same. Not pretty much, it stays the same. Sorry. All right, so the currents I are all the same through R1 and R2. Here, I can name this to be sigma R. คุ้นๆไหม อันนี้คุ้นๆไหม All right, so when I say I can name that R1 and R2 to be like a single sigma R, this is what we can say that I am finding an equivalent resistance. Equivalent. When I say equivalent, equivalent means if I want to imagine that these 2 resistors to be just only like a single resistor, how much resistance should that single resistor be? Okay? All right. And that's how you can pretty much, you know, get rid of complicated structures of resistors and reduce down to like a single resistor and use simple Ohm's law. I'll show you what it means here. Here we go. So let's add some more to it. So if I have R1, R2, and R3. So everyone seems like, oh, okay, done. I know that the potential across this one is going to be IR1. Potential across this R2 is going to be IR2. Potential across this one is going to be IR3, yeah? However, now we know these 3 potential difference will add up to E. That must be. Okay, that's what it is. So I can say E is just the potential from these three devices. But they're all sharing the same current, so I can pull out the common factor I. Now you have only the summation of the R. And once again, you see that if I'm going to reduce that R1, R2, and R3 to be a single resistor, I can name that equivalent resistor having an equivalent resistance of R1 plus R2 plus R3. And now your circuit can be reduced down to only these simple circuits. Okay? And by going through this, you're starting from 1, it's followed by the 2 R's. Now with the 3 R's, now you can imagine if you have a series of R, then your equivalent resistance is just going to be the sum of all those resistance. Okay, sounds good. All right, so if this is good, we call this resistors in series. All right, back to back. Okay, every time you have a series of R's, you can wrap it up into a single R with the equivalent resistance of the sum of resistance from each individual resistors in series. Okay, cool. Not bad, not bad, not bad. Next. On the other hand, บอกอาจารย์ I might don't want to put R in series. I don't want to put them back to back. I want to put them sort of like spreading out. I want to split them. When I say like split, look at this. Look at point A and B now. So when you have two resistors, R1 and R2, instead of put them back to back, you say you put them side by side. So you take the left end of the R1 and R2 and wrap it into a single point. You take the right end of the two resistor and wrap into another point. In this case, you have a parallel connection. Okay, they are side by side. And the things about this one that different from the series is because now you have here junction. Ooh, whoa, sorry. You have here. This is junction. When we say junction, what does it mean? It means here, the current flow out. Let me call it a capital I. The capital I come out. Zoom. Now you hit the junction. If this were water, you have to split, right? Some part of the water will go left, some part of the water will go right. Same thing with the current. Electric current will do the same thing. So there will be a portion of the current go left, and some of the current will go right. Okay? And of course, no matter what happens, the I sub 1 that go left will go through the upper R. The I sub 2 that's go right will go through the R sub 2. All right? At the end, it will have to combine back again. So I sub 1 and I sub 2 eventually will come back together and join the capital I one more time. Conservation of charge. Okay? You cannot get rid of any charges in your circuit, or you cannot create one in your circuit. Everything has to be conserved. But during the movement, you're going to have to split them a bit. All right, now, what I can ask is this. What is the potential across R1? Well, Adan, that's not bad. If you want the potential across, it's going to be I1 R1. What is the potential across R2? Well, Adan, it's going to be I2 R2. Because calculation of potential is simply the product between the current and the resistance. However, look at this one. Because we just said the current flow total must be equal to the current for each path. The upper path and the lower path, I1 plus I2. So what actually I can say about, wait. I1 R1, I2 R2. If you look at the bottom of this one, how can you match or how can you compare the I1 R1 and I2 R2 with the potential from the battery? What do you think? Well, Ajahn, actually, if you look at the bottom half of this one, whoa, it's still that same E. No different, okay? With me, guys? So what I'm saying over here is, because no matter which path you are looking at, you can look at, let me draw you this, the upper path, okay, the middle path, it looks dirty a bit, oops, sorry, okay, I just want to show you this, okay, here we go, see, so you can go upper path, the green path, you can go the middle path, the yellow one, or you can come down in the bottom. They're all connecting point A and point B. So that means what you are looking at right now is I1 R1, that's upper path, I2 R2, that's the middle path, E, the bottom path. This must be the same potential difference across. Okay, cool. So from this, it means actually you can calculate I1 and I2. I1, if you pair this with the E, so okay, let me write it like this. I1 R1 is also E. I2 R2 is also E. They're both equal to the E. So that leads you to I1 is just E over R1. I2 is just E over R2, yeah? So you know exactly how to calculate the current flow through each resistor. Very good. Then I can use this result, plug it back into this. So I can say the full current, the total current flow in your circuit is just I1, which is E over R1, plus I2, which is E over R2. But the E is just common factor I can pull out. And I'm left with just 1 over R1 plus 1 over R2. Does it look familiar? Yes. You can now wrap this one into a single resistor one more time. And you can just name this one, it's just 1 over R equivalence. So you're doing the same thing just like what you just did with the series connection. So you can wrap this thing into like a single resistor. So your circuit will look just like this now with the single equivalent resistor on it, and you're done. You can actually extrapolate this idea into multiple R. You can do R1, R2, R3, blah blah blah, on and on. So that's why you can get to this formula for the parallel connections. Sounds good? Oh, I forgot, let me plug in the battery. Just a second, guys. Where is my adapter? Oh no. Okay. Right here. Alright, got it. My notebook is about to shut down. 1 second. Okay. I hope it's in time. Alrighty. Oh, all right. Okay, guys. I'm back. Okay, so I think maybe this seems a bit too long for those of you that are familiar with this already, but I hope this works for those of you that haven't done much of the circuit analysis. So in conclusion, from what we can do is let's practice on this one. Right? So from now on, if you have sort of like, you know, multiple of the resistors in your circuit, what you can do is find the single equivalent resistor. And all you need to do is just evaluate the resistance of that equivalent resistor. And then you can wrap, sort of like reduce your circuit down into a simple circuit. Okay, for example, like this. They say find equivalent resistance between point A and point B. So what you can do is just start from whatever that you want to make it cleaner. You can see that this 4 ohms, okay, and 9 ohms are already connected in series. However, these two, 7 ohms and 10 ohms, are not. It's still in parallel. Okay, if you can think of this is like 2 points over here. So first step, if I'm named these 2 points to be A and B, what I can do is just reduce this one into a single equivalent resistance first. So what I can do is over here is I can see that 7 ohms and 10 ohms are connected in parallel, right? They are side by side. So I can reduce this one down into 1 over R equivalent equal to 1 over 7 plus 1 over 10. You guys with me? Okay, and then I can work on this number a bit. It's 17 over 70. So that means your R equivalent is just 70 over 17. Number is bad, all right? But I'm just gonna keep it in that ratio format there. Okay, so once you can find the equivalent resistance of these two, now your circuit will look like this. You guys with me? A and B stays there. That's still A, that's still B. Okay, 4 ohms still here. 9 ohms still there. But then the one in the middle now is 70 over 17 ohms. All right, got that one. And then once you have this done, then you can do one more reduction, because now these three are just in series. It's just back-to-back connections. So you can now wrap it into a final single. Let me call this R equivalent prime. That's the second one. So what you get from this one is now your R equivalent prime is just 4 plus 70 over 17 plus 9 ohm. And that's it. You're done. When I say done, mean now you can reduce those 4 resistors into a single resistor R equivalent prime. And when you deal with part B, that will make it a lot easier when they say, hey, if you introduce potential difference of 34 volts between point A and B, what is the current in each resistor? Sorry, A and B is down here. I just saw that I also use A and B. Sorry, okay. Their A and B, not my A and B. All right. Okay, so if you apply potential difference across the problems A and B, not mine A and B. Sorry, guys. I didn't notice that there is A and B there already. Okay, so it's like you connect this 34 volt generator, okay, through A and B in the problems, and that lead you to calculation of your current flow simply by taking that 34 volts divided by R equivalent prime that you just calculated, and then you know what is going to be your current flow in the circuits. Okay, sounds all right enough to do the equivalent resistance calculation? Yeah, sounds good. Okay, so at this point you only have 2 types of connections when you have multiple resistor in your circuits. It's either back to back, that's series, or side by side, that is parallel connections. And then you know how to find equivalent resistance of each connections. Then you just keep reducing it down until you end up with just a single final equivalent resistance. And then you use that along with the Ohm's law. You can calculate the total current in your circuits. Okay, so I think this is easy enough for you guys. Let's do one more. All right, we're almost there. And we will have enough reviews that allow us to do Kirchhoff's rule. Okay, so let's do one more. All right, I don't want to focus too much on this because the goal of this one is Kirchhoff's rule, not equivalent circuits. Okay, consider the circuit shown. Find the current in the 20 watt I think 20 ohms. I think this is rendered incorrectly. Okay, 20 ohm resistor. And part B, what is the potential between point A and point B? All right, so I think this is maybe the most complicated problems up to this point. I think this is the hardest one, but it's still not too bad. All right, let's go through this one. They're asking you to figure out the current flow through the 20 ohm resistor. But the circuit looks kind of messy a bit. I can rearrange them to make it a little bit cleaner. So let's sort of follow me here. So I have 10 ohms on top. I have 25 volt here. But look carefully. Let's try to draw like this just to, trick your mind a little bit. But point A over here is the same thing as point A over there. Doesn't matter. You can move things around your electrical wire without changing anything. Okay, you can place your A anywhere you like. They are still point A and B anyway. They're all the same. No change. So actually, if I'm focusing on this portion of this junction over here, I can wrap that junction down into this. Okay, focus on that point A. So my point A is here. Okay, think of this big junction over here. You have this wire, and that wire. So actually that junction will have a three-way split. Okay, so what I can draw over here is I can draw this. That will be the upper junction. That's the 10 ohms right here. Okay, the one that's pointing down next to this one, it go through the 5 ohms. That's this one right here with me. And the leftmost, the third junction, actually you can come down here, and on this one you have 2, because when you follow through this third junction over here, you have to go through 5 ohms and 20 ohms before you arrive back at point B. So there are 5 ohms over here and 20 ohms over here, and everything will lead you back to junction B on the right. So everything come back to this B, B, and B. Okay, you guys with me? So this is a rearrangement of the circuit to make it a little bit cleaner. All right, and for those of you that want to draw it in a different configuration, that is more than fine. Some of you might find it nicer to draw it like this. That is good too, actually, to make it feel more parallel, pretty much, if you like. That's your A, that's your big junction B right there. 10 ohms, 10 ohms, 5 ohms, 5 ohms, and 20 ohms. Here we go. Okay, so it depends on what you like. Okay, depends on whatever you feel want to draw it. As long as you keep the configuration the same, it's fine. Okay, here we go. So what's next, guys? What can we do? This one is very, complicated in the sense that you want to know the current actually flow through the bottom wire. This is what you want. Let me call this I3 then, because there will be I2 here and there will be I1 there. All right, because this junction split into 3 ways. So each way will have its own current. Let me name them I1, I2, and I3. The question that they want is, what is I3? That's the questions, of course. And next, they want to know what is the potential across A and B. So let me name the total current here is just I. Okay. So how to proceed, guys? Of course, because first of all, before you can do anything else, you probably want to figure out what is the total current in your circuit first. Sounds cool? All right. So if you want this, what I need to do is just reduce that crazy stuff here into a single resistor, equivalent resistor. So first of all, what you can see is in the bottom, these two are connected in series. Okay, so actually I can wrap this bottom into a single one if you like. So I can draw the circuit to have it look like this. Okay, there. With me, guys? Okay, so 10 ohm is still there, 25 volt, 10 ohms, 5 ohms. This one 25 ohms. Cool. All right, now once you have this, then you can start seeing that these three sorry, are connected in parallel. They are side by side. Okay, so keep going. So what I can do is now, oops, sorry, let's use black. Here you go. Oops, it's still red. All right, here we go. All right. So you have 10 ohms with the 25 volts. Now you can reduce everything down into a single equivalent circuit right here. Let me call R equivalence for now. Okay, and that R equivalence over here can be found from here because they are in parallel. So 1 over R equivalent is just going to be 1 over 10 plus 1 over 5 plus 1 over 25. You guys with me? Okay, because these three are connected in parallel side by side, I can wrap these three into one single equivalent resistor by doing this reciprocal sum, is the inverse sum. Okay, so I can work on this a bit. It's 55 times plus 10 plus 2, 17 again. So equivalent circuits over here is going to give you 50 over 17. Wow, number is bad. I don't like 17. Okay, that's prime. Okay, very good. So my math is correct, I hope. Okay, 17. All right, so that's from the parallel connections within your circuits. And now the last two, guys, almost done. I can see that this is also parallel with this again. Okay, and that will lead you to final configuration of this, which is I can keep 25 here on top. Here we go. Let me call this R equivalent prime. I want to sum those two together. It's simple now because it's just 10 plus 50 over 17. 25 volt. Okay, guys. So I hope you see the whole process of reduce the whole thing down into a final single equivalent resistor. Okay, you sort of match any pair or any pack that you know the type of connections very clearly. If they are in series, you wrap them into a single one. If they are in parallel, you wrap them into a single one. Do until you have the last equivalent resistance. With that, then I can answer now what is going to be total current in your system is going to be 25 Ohm's law over that R equivalent prime. Very cool. Alrighty. Very nice. Now the hard part is what is the current just going through the bottom wire, I3, right? That's the hardest part. However, actually, if you look carefully on this one, actually answering part B seems to be an easier, not easier, but actually you need I mean, if you go through the part B, it seems like that will help quite a lot. What I'm saying over here is this. You guys look at the point A and point B. Okay, point A and point B. No matter where you are, point A and point B is still there. It just look a little cleaner and cleaner and cleaner. Okay, so let's answer part B first because it's already there. Do you see what I'm seeing? Once you get the once you get the total I current flow in your system, that's I. See? If you look at the bottom left circuits, you can calculate the potential across point A and point B right away. Because here we go, V, A and B is just I, your total current in your system, times just the R equivalent from the previous circuits. Not the R equivalent prime, just R equivalent. You guys with me? So actually, the lower left circuits allow you to calculate the potential across point A and B very easily. You guys with me now? Okay, now? Okay, now? All right. Okay, so why do I say that it seems to be better to figure out V between A and B? Because once you know the potential across A and B, voila, do you see something here? You know the potential across A and B. You can use that to calculate on either wire along this one because it's V between A and B. You can use that to calculate what is going on the top wire, the middle wire, or the bottom wire separately. Because no matter which path or which wires that you try to use to calculate one more time. No matter which wire you try to calculate the V, A, and B, you'll get the same numbers. Because they are the same point A and B, right? You have three choices now to figure out V, A, and B. So what I'm saying is, I1 times 10 is still V between A and B. That's the top wire. I2 times 5 is still V, A, and B. Or I3 times 25. Oh, it looks bad. Sorry. Let me write it nicely. I3 times 25 is still V, A, and B. You see what I'm saying? So actually, by knowing this, you can calculate the current flow on each wires in these parallel connections. You can use V between A and B to calculate I1, I2, and I3. And that allow you to calculate, in this case, I sub 3. That's part A question. Okay, you guys sort of with me? I think this is going to be the upper limit in terms of the Ohm's law circuits or finding equivalent resistance problems. I don't want to go beyond this one. But the reason that I picked this exercise to try because this sort of go around back and forth between how to calculate the current through the Ohm's law, how to calculate the voltage using the Ohm's law. I mean, you're still working around V equal to IR, Ohm's law. There are no other things. However, the understanding about this one is just, hey, every time you're talking about 2 points, A and B, and no matter which type of connections you have, potential across A and B is still potential across A and B. If this one has a three-way split, the potential across each wire must be V, A, and B. So you can use this fact to calculate the current flow on each wire, something like this. All right, and if there's no junction at all, if it's just a straight line, like a series connection, V equal to IR, that's Ohm's law. I mean, everything is Ohm's law, but it's just the matter of the configuration of the circuits, right? That you have to add a little bit of understanding of the structure of the circuit into it. But whenever you look at each individual part of the circuits, you still apply Ohm's law anyway, V equal to IR. Okay, sounds reasonable. I hope you guys are very quiet today. All right, so I think it's a good place to stop.